My name is Magdalena Musielak. I'm a senior lecturer here at the Mathematics Teaching and Distance Learning Center. And what I want to tell you about today is the fundamental theorem of calculus. This is a theorem that we use all the time when we evaluate definite integrals, but very often not fully appreciate its importance. Now, I don't want to give you here a formal proof, but rather an intuitive derivation of it. Now, the fundamental theorem of calculus is appropriately named because it establishes the connection between two major branches of calculus: the differential calculus, which arose from the problem of finding tangents, and integral calculus, which arose from problems of finding areas. Two seemingly unrelated problems, and yet very tightly connected. On a historical note, it was Newton's mentor, Isaac Barrow, that discovered this connection between a derivative and integral, and then later Newton and Leibniz explored the idea and discovered or developed calculus as we know it today. The crucial concept of understanding and deriving the connection between a derivative and an integral is that of something called area function. We start with a continuous function f, much like this one, and some fixed point a. Now our area function will be denoted with a of x, and it will evaluate the area between the graph of the function f, the t-axis, on the interval from this fixed point a to some variable point x. So this area here, that is something that we will denote with a of x. Now this area is of course a definite integral in the limits from a to x of our function f of t dt. Now x here is the variable, is the independent variable of our area function. At the same time, it's the upper limit of integration. So for my variable of integration, I have to use a different letter, so-called dummy variable. So here I used t. I cannot use x anymore. You can use ws, whatever your pleasure is. Let's look at how this function works maybe. There's a little, if you look at this little animation here, you can see how the function works, which means as we choose different values of x, we set the various upper limits, then the area changes, so the value of the function changes. And notice when x is set to equal a, which in this case is 2, we evaluate the integral from 2 to 2, which is simply 0, of course. So the value of the area function at a, at the starting point, is 0. Now back to our general picture here. Let's pick another point a little bit to the right of x, and let's denote it by x plus h. So this little distance here is h. Now, according to my definition of the area function, then maybe I'll write it here. A of x plus h is the integral from the starting point to this new endpoint of f of t dt. So a of x plus h is the area of the region from a through x plus h, on the interval from a through x plus h. So this area is a of x, the big area is a of x plus h, so this area here, that is actually the difference between the large and the small areas. Now if h is small, then this region is nearly rectangular. So actually, this region can be approximated by a rectangle with base h and height f of x. So I can write that a of x plus h minus a of x is approximately the exact area of this little strip is approximately the same as the area of the rectangle h times f of x. I'll divide both sides by h here. And now notice that if h gets smaller, this approximation actually gets better because this little strip gets thinner and thinner. So as we let h go to 0, if we take the limit, we will achieve an exact equality here. So if I take the limit of both sides, I should get exact equality. And now this is the amazing part. This is where you should notice what you have here on the left is a derivative of a function a. This is exactly the definition of a derivative. So this can be written as a prime equal, now on the right here we have a limit of a function f which has nothing to do with h. So we have simply f of x. This is the amazing connection between the derivative and the integral, because after all a is an integral. This says, let me move the boards here. This can be written using Leibniz notation as d dx, so that's instead of a prime, of our function a equals f of x. This is the first part of the fundamental theorem of calculus. It says that the derivative of an integral of a function is this function evaluated at the upper limit. This is where the connection comes in, and this expression here you should recognize as a definition of an antiderivative, because if a prime equals f, that means a is antiderivative of the function f. Now, having established that, this is something called first part of the fundamental theorem of calculus. Now we are just one tiny step away from arriving at this powerful formula, sometimes called Newton-Leibniz formula, that we use all the time for definite integrals. Because if we know that a is the antiderivative of f, that means any other antiderivative of f differs from a by just a constant. Because antiderivatives, there are infinitely many antiderivatives, and they differ really just by constants. They are copies of one another. So if we take any other derivative, antiderivative of function a, the difference between capital F and a will be in a constant c. Okay, so let's evaluate the value of that function at b minus the value of that function at a. By what I've written above, this will be a of b plus c minus a of a minus c. Now c will cancel. If you recall from this little animation, a of a is 0, and we are left with just a of b. Now this is quite amazing, because look at what we got. We got a of b equal, by definition, area function is the integral from a to b of our function f, and from this calculation it's the difference of the values of any antiderivative of our function small f. This is the second part of the fundamental theorem of calculus. It's a simple derivation, and you arrive at a formula that allows you to integrate any function in two simple steps. Find any antiderivative, evaluate it at the endpoints, and you're done. This theorem is by far the most important theorem of entire calculus. Because if you think about it, before Newton and Leibniz came up with, explored this idea, before Barrow came up with this theorem, people who were able to solve problems like finding areas, volumes, lengths of curves were considered geniuses. And now, with the help of this little formula, we can all do it any day of the week.